Good afternoon. I appreciate everyone here, especially other than the Lockheed people that are in the room, which there is a good crowd of you. I appreciate that. Again, my name is Paul Foster. I'm a software engineer and product lead at Lockheed Martin here in Orlando. And I've been in the simulation software development business for 25 some odd years. And one of the biggest challenges we have is getting proper military doctrine encoded in our behaviors in our simulations. And so that's what our talk is today. Dr. Gita Sukthankar from University of Central Florida. We've partnered with them to get behind the science of LLMs and generating this kind of content. And so without further ado, let's get started. So the topics today are, I'm going to go over what we mean by military doctrine. I'll go into the solution architecture and our agent approach. We'll give some example prompts, and then I'll hand it over to Dr. Sukthankar to talk about large language models in general. This is, and a conclusion, of course. And this is largely sort of an inspirational speech. This is not, this work is in progress. So I don't have software to give to you today or a plugin that you can download from the fab, but we hope this inspires a lot of teams to collaborate and look into the same kinds of technology. So what is military doctrine? Real world behavior is the goal. So in the simulation and training industry, it's important that our automated units and our individual soldiers, our vehicles, behave as close to the real world as possible in terms of their behavior. The visual realism is a nice to have, and it's what gets the soldiers and trainees into the seats of the simulators, but it's really the behavior that keeps them in the simulator. If you had let's say a officer that was trained at West Point in the classroom and he learned how to do troop leading procedures, right? And then he gets into a simulator and finds that the troops he's leading are not behaving the way he expects, or the adversary is not behaving the way they also expect, they're going to immediately assume that there's no credibility to the simulation. And that is a real challenge that we have, is gaining that credibility with the customer that the simulation we're selling them, they can trust. So we spend an inordinate amount of money and time in this process of sort of validating these behaviors. And that includes the doctrinal references that we need to go back to and prove that, hey, it says here in this document that the process for moving in formation requires, this type of distance at this, angle. And then we can demonstrate that in the simulation. But the process is not cheap and simple by any means. So what is military doctrine? What's included in that kind of concept? And here's a few examples. One is how forces contribute to military operations, major operations, battles, and engagements. Within the U.S. Army alone, actually, before I get to that, the U.S. military doctrine, by the way, is openly available. Most of it is openly available on the internet, and it's used by many other countries, including some of our adversaries. And within the U.S. Army doctrine alone, there's about 400 documents that describe individual soldiers and how units should perform military tasks. They're more than just how to fight. They're how to support the fight logistically, how to organize, and how to utilize different types of technology, assets, and capabilities within their units. What means should be used? How an entirely different field manual, the infantry, rifle platoon, and squad describes movement techniques like how to move in formation. How forces should be structured. In the US, tank platoons are organized into 4 tanks, and they usually move in pairs, right? 2 pairs. But in other parts of the world, they use 3 tanks, so they don't organize in that same kind of fashion. So the doctrine needs to respond to, the country, the type of force, and so on. And then where forces should be deployed. So within different behaviors, sometimes you'll have a portion of the unit that needs to be deployed into an overwatch type of position. When, where, and how that movement needs to take place is all part of that behavior. Modes of operation or modes of cooperation. I'm going to go down here. Modes of cooperation. So modes of cooperation. So this is really referring to how responsibilities are shared between different armed forces or between different types of forces within the same armed force. So an example would be infantry is often supported by artillery units, right? But that cooperation and communication needs to happen and be encoded in the behavior. So this size, complexity, and the volatility of this military doctrine requires that we need a solution to encode that behavior in the simulation that not only shortens our AI development time, but also assists in providing us doctrinal references in those generated behaviors. So it's not good enough to just have the behavior on the shelf. We need to prove, again, back to the customer that it's accurate. So what's the solution that we're looking at here? We start with taking military doctrine and using it to fine-tune an LLM, and then add additional context like behavior tree syntax and semantics, the behavior tree schema, and by that I mean the specific implemented nodes, conditions, decorators, or whatever form, whatever implementation you have, as well as a data set of behaviors that also can help to fine-tune the LLM. Obviously, the generation is behavior trees, but it's more than just generating them one time. We need to maintain them, we need to adjust them, and we need to make changes. So, but to really make sure that we improve upon this process, reduce hallucinations, and we need data from real behavior data sets. The data sets we're using right now are based from the robotics domain because that's the large set of behavior data sets that are available. But going forward, ultimately, we need to find new ways to train these. And Dr. Sukthankar has investigated some of those, and then that's part of the work we're trying to do. Okay, so part of our multi-agent planning approach introduces 3 kinds of agents in our solution. The first is an entity agent. Now, this is a type of agent you're probably most familiar with. This governs the actions of a single human, a vehicle, aircraft, animal, what have you, right? Our next type of agent is an entity unit. So this is logically an agent who's really just in charge of other entity level agents, right? But we have a third type, which is an aggregate unit agent. So he's in charge of other aggregate unit agents or other entity unit agents. Now, why would we make this so complicated? Well, there's a very good reason, and that is that the communication that happens and that needs to happen between these types of agents is something we can model from the real world. So in the military domain, the flow of communication down from let's say a platoon to its squad to individual soldiers is a very logical and very methodical communication process in the form of orders, commands, and then the flow back in terms of reports. Right? So we want to not only model that communication in terms of the physical communication, the radio aspects, but also the ability to separate our agents logically so that at each level, an agent implementation at the entity level doesn't need to be concerned with the implementation at the entity unit level, for example. So on the right-hand side, you can see there we have a platoon aggregate unit agent at the very top, who's controlling 3 squad-level aggregate unit agents, which are in turn in control of 2 fire team entity unit agents, and they're in turn each control of a entity-level soldier agent. So you can start to imagine that even at a platoon level, the scalability of this problem is just, it gets out of control, right? So when we talk about some of our larger simulations that go into the orders of battalions and higher, we're talking about literally tens of thousands of different agents, right? That could be added up here. All right. So part of this communication that I mentioned, you can imagine, let's say that we have a platoon that is implementing an attack order, right? Part of the implementation of that behavior is sending an order to the squad to dismount. The squad agent then in turn sends orders to the soldier agent to move, right? Maybe after they've dismounted, they need to move into position, find cover, that sort of thing, right? So that communication flowing down and then the reports going back when those things either complete or maybe they fail, that all needs to flow into the next level behavior tree. But I don't know if you noticed, but the 2 boxes on the left are behavior trees, but the one on the right is a state tree. So part of our architectural approach is that we keep each implementation separate enough so that we can do that. We can swap out and choose different agent implementation approaches. And so at the bottom level, we've chosen a state tree, for example, at the soldier level, but using behavior trees at the upper two levels. Now, with all these different sort of agent implementations at different, what we call echelons, you're going to need to specify exactly what that schema is. What are the allowable nodes that you can use within those implementations? So this idea of a behavior tree schema is what I'm kind of circling there with AI unit or AI entity. Now, state trees in Unreal have this built in, where you can build a state tree and then select a predefined schema. And that schema limits exactly the nodes that are presented to you when you're defining a task or selecting from a task or selecting a condition and so on. There is an equivalent in behavior trees, but you can see the importance and the need of that kind of thing. So as part of our implementation, when we define that schema, we will have some tasks, some conditions that actually work at multiple levels. Like if you enemy detected, right? That could work on either of the unit levels and maybe even at the entity level. And so that schema can control where it's allowed to be used. Okay, so variation. There's been other talks I've heard today about variation. This is a common problem in games as well. And for us, it has some other unique challenges. So one of those variations is skill level. For example, at the unit level, does a force know how to move tactically in formation to maximize its readiness? Or at the individual level, does he or she know how and when to find cover? Capabilities. Does the unit possess the ability to communicate immediately? Does it have radio communications, in other words, or does it only have hand signals or voice, right, among its subordinates and peers? Another example, I mentioned indirect fire or artillery. Some units are deployed with artillery equipment that they can use to suppress the enemy, others do not. So those capabilities need to be utilized in the behavior when they're available. Organization structure. So I mentioned the tank platoon organization as an example. In that case, when I have a tank platoon, I have those 4 tanks. I need to make a choice. Do I want to move all 4 of those tanks in formation together, or do I want to split them into 2 groups and move them independently, right? And that's one of the behaviors that we focused on a lot recently, is this concept of bounding overwatch, where you move a pair of tanks in formation into a secure position. They suppress an enemy while another pair of tanks moves around. Unit type. So when we talk about an attack behavior or a move order, we still have to qualify it by what type of unit is performing that action or that behavior. So a combat unit might move and prepare for attack very differently than a combat support element like a convoy unit, right? Or echelon. So I mentioned platoon attack versus company attack. There are some similarities. Both types of units can perform that function, but the orders that they give to their subordinates are very different. So all of this leads to behaviors that can become very resistant to change just from the sheer complexity and the number that we have to manage. So a key part of this tool and this concept has to be this concept of refactoring that we apply all the time in code, but we need to be able to do it in behaviors. We need to be able to make broad sweeping changes across a number of behaviors. We need to be able to take a behavior, cut it in half, and create reusable behaviors or composable behaviors that I can apply in multiple places. So it's a big problem if you think about all those other ways in which we need to use this kind of concept. So here's our kind of picture of the solution. What we've got is an Unreal plugin that works alongside of the behavior tree editor. So you bring up a behavior in the normal fashion, and we present a button where you can say, okay, I want to edit this using the tree builder, which then loads that behavior into the same looking editor, right, as the behavior tree editor, but it adds that prompt window on the right-hand side. The prompt communicates with the back-end service, the prompt application, which is composed of three key technologies. One being the LLM is the most important, right? A foundational model, tuned with a low rank adapter model, and primarily tuned on the behavior tree data set that I mentioned. And right now, again, we're using robotics behaviors. and then a retrieval augmented generation, or RAG, which is parsed from the military doctrine itself. So the RAG is, of course, what gives you those doctrinal references in the response in your behavior tree response. But you can see there's a couple check boxes there for you can choose to say, do I want to serialize the tree and send it to the LLM? Do I want to get a response back? You can do either of those types of things. And when we first started working on this, we had hoped that we could do this with state trees, because we've already transitioned, LLM has already transitioned to using state trees for the primary number of our behaviors. But when we started this work, state trees were brand new. I mean, we started when they came out in Unreal 5, whatever, and they didn't have an easy way to serialize. Their editor functions were not easily exposed in the code, right? So we couldn't build this kind of easy to build editor. So we said, all right, let's just do it on behavior trees, because we have all this support in Unreal existing, and there are data sets out there on behavior trees, right? So, but there isn't an equivalent for state trees yet. So, more work to be done. All right, next let's take a look at a couple of prompts, examples. So let's say, for example, we write, here's the prompt: to write a behavior tree for a platoon organized into 2 vehicle sections and 3 dismount squads. The environment is urban and the temperature is over 100 degrees. The behavior should include the platoon moving along a route, dismounting the troops at a given location, and performing a search of nearby structures, and then neutralizing an enemy. Once complete, the platoon should continue on the route and assemble at a designated area. So, a portion of that tree might look something like this, right? Along the left-hand side, the movement would evaluate, do I have roads available, right? Using that is roads condition. If so, perform a road march. If not, move tactically, which is a fancy way of saying move cross-country. But in this case, this is the orders that are going to be sent to those vehicle sections, to the vehicles to actually move, right? So imagine the squads are mounted in the vehicles, and now the vehicles are moving down either roads or cross-country. And these tasks are waiting for those subordinate units to finish those orders, right? When they're finished, the tasks here will complete at this level, and then that'll transition us in sequence over to the occupy assembly area. So this is where the vehicles kind of spread out and they get into a certain position that's suitable and protected for the dismounts to get out. So the soldiers then get out of the vehicles, they find good cover positions, and when they're all done with all that, we transition over to this parallel set of tasks that coordinates both the soldiers dismounting and the vehicles waiting for the soldiers to dismount. All right. So another thing to note here is that, whatever schema you use, and this is true in code generation with copilots and so on, is the specific syntax and semantics of your particular nodes. Like the dismount node you can see there, the task is actually mount, but we pass in a flag indicating to perform the dismount. So that sort of nuance has to be accounted for in the LLM. It has to understand what that means so it can properly encode that in this portion of the tree. All right, another example is my last example here. So let's say that we have a tree and we've got this small portion here that has this move tactically, and we want to modify the tree so that the unit takes cover if fired upon. So the first condition is under fire, is triggered, followed by the find cover. But in this case, you can see there's no description. So we also want this concept to work where the LLM can propose tasks that we need to implement. And so that's this example here is where there is a move tactically task in existence, but there was no is under fire or find cover type of task. So the LLM proposes those nodes, leaves a placeholder for them, and then adds some description that tells you, hey, you might need to do more here. There's more information you need to do. Here's some doctrinal references that you can use to help define that, and then you can iterate from there. All right, so I've taken up enough time. I'm going to hand it over to Gita to perform the rest. Thank you.
So Paul gave you a really great description of our current ongoing work. But for this part of the talk, what I'm going to do is two things. I'm going to talk about some things that you should consider as a developer using large language models and applying them to different types of game applications. And then I'm going to talk to you about a project for which we've already published. The code is available. The data set is available. It was not done using Unreal. It was actually done using StarCraft 2. And the reason Paul alluded to in his talk that because of the tremendous amount of data available for StarCraft 2, that was a logical starting point. So in the old days, I might have started this talk by trying to tell you what a large language model is, but now I'm confident that you all know what a large language model is. And not only do you know what an LLM is, but you also regularly use one. So just kind of a quick show of hands, how many of you regularly use any of the GPT models? Okay, that's the most fun. Meta's Llama models? Okay, Meta's Llama models are probably the most popular for academics. Google's Gemini and Gemma models? Okay, less so. And then our newer DeepSeek. So essentially, that you have probably noticed that every week, new models emerge from different companies. And every week, we see some turnover on the leaderboard. So that if you look and you follow research in the LLM field, that there are various leaderboards for different specialized tasks, language comprehension, coding, various things. And the leaderboards like shift a little bit. But I wouldn't advocate as a developer going out, running out, and getting basically the model that is currently best performing on the leaderboard. There are many other facets to consider, not the least of which are more prosaic deployment considerations like the latency, ease of API usage. But one thing you have to take into account is most of these large language models were trained with the specific goal of doing kind of chat, multi-turn dialogue applications where someone is kind of typing into the LLM in a free-form conversation. When you're looking at the case of using a large language model to generate code, plans, other types of game content, that's probably not what you want to use. You do better if you use a model that was either fine-tuned for instruct, to follow one-shot instructions, or a special purpose coding model that's been trained with a higher percentage of open source code. A second consideration is really open source or closed. Would you rather use kind of a model that's already, the code has been released, the weights have been released, you can download it, you can run it on your own computer, or would you rather use one of the closed models? Typically, the closed models are the more powerful models, but often come with the increased pricing. You might get the better bang for your buck by essentially going with a smaller open source model which you configure for your special use case. Of course, there's the eternal question, how much does size really matter? So for our research, we've used smaller models between kind of 2 and 8 billion parameters, but the larger closed models may have about 1 trillion parameters. And I will say this, if you are interested in multimodal applications, so combining vision, language, that kind of thing, you are going to need a larger model inherently. If you're more interested in utilizing complex prompting, having the model explain itself, you will probably do better with the larger model. For other cases, you might do fine with a smaller model. The smaller model will probably help you more in the pricing department, typically done by input-output tokens, some just kind of by monthly subscriptions. Another kind of last thing to consider is the size of the context window, because context is very important. So not really just the overall number of parameters, but the amount of input that model will support may be the best indicator of your performance. So in in our lab, typically, we are looking at diverse application cases that are a little bit off the beaten path. That if you're looking at the case, you're trying to do something that does not match what the model was trained for, you will probably need to customize your model with fine-tuning. And this can be done with the closed models. In some cases, the APIs do support some amount of fine-tuning, but often it's best if you use an open model and then you can delve into it and use a variety of these parameter-efficient fine-tuning methods, of which absolutely the most popular two methods are LoRa, low-rank adaptation, which is what we're using in this project, and quantized LoRa. So the key thing about these models is that they are enormous. They have a lot of parameters, and those parameters were fitted with data, enormous data sets. Chances are that you will be relatively starved of data. For your specialized application, you will not have very much data. If you don't have very much data, and you're trying to fit 1 billion parameters, you're in trouble because you might have had 10,000 data points, but now you have to make adjustments to 1 billion numbers. You don't really want to do that. So what LoRa is doing is essentially saying that we're going to keep and freeze all these lovely pre-trained weights, but then we're going to add these specialized adapters. But we're going to make these adapters particularly parameter efficient by representing them as the product of two low-rank matrices. It keeps the number of parameters that you're trying to learn with the training data very small and enables you to fine-tune for a specific case. You have the adapters, and as a bonus, you can swap them in and out. If you care about performance, you can also kind of add the adapter directly in to improve the latency. But this essentially is one of the best ways to customize your model. Now, it may be that you really just don't have enough data to support fine-tuning. So then it's all about context, context, context. Adding context, particularly for coding style tasks, is what will help you the most. With probably the most popular context addition method is called retrieval augmented generation. So that's essentially the method that we've been employing in this project. In this case, you assume that you have kind of a small database of documents that you want to draw into. You create this database of the documents, represent them in a large language embedding. And then when a new query comes in, what you're going to do is essentially you're going to try to identify which documents in your data set are similar to the query. And then those documents get pulled into and automatically added into the context. So the generator has that information in the context when it considers the output. And basically between these two methods, LoRa and RAG, that really covers most of what is useful. Other kind of fancier methods like contextual activation vectors and so on may be useful, but these two methods will cover the majority of your use case. Now, what I'm going to tell you about, so I guess I should ask, are there any StarCraft 2 players here? Okay. So this is a project that was done by my PhD student, Junaid Khan. And what we were looking at was the use of a large language model for build order optimization in StarCraft. So this model does not actually play a full game of StarCraft. There is a group out there that created an LLM that plays StarCraft through a text interface. We found that to be not a great project because of the latencies. So it's really hard to have your LLM go fast. We can do the build order in a reasonable time, but to do all the StarCraft actions is hard. So in this project, what we do is we use a large language model that's been fine-tuned to generate these build orders, which to some extent you can think of a build order like a plan. It's telling you what units your StarCraft player should be creating over the next few time steps. We used a very small LLM, Microsoft's Phi-2. It's only 2.8 billion parameters, and it was constructed with a couple of stages of fine-tuning. One, to get the model to learn general StarCraft knowledge, and then the second to do specific build orders. So if you look at the picture of the model, the snowflake shows the frozen stuff, the large language model is just vanilla Phi2, and then everything marked with a flame is the trainable section. So probably the greatest amount of work in this project was for my PhD student to go and assemble this text data set of kind of general StarCraft knowledge. So what we did is we created this question-answer data set, and that's a common training method. Essentially what you're doing, you get this data set, and then you're training the LLM to be able to generate answers to these kind of questions. So our questions are specific to StarCraft races, StarCraft unit types, StarCraft tactics. And so in this data set, we included some example build orders, but not that many. So this helps us in this way. So when we prompt the model, what are the build actions for the Terran race? If you just ask that question to the generic Phi2 model, what it would do is it would show you that it has a decent knowledge of how real-time strategy games are played. It understands that common things would be, build a barracks, do some research, build a space station. The phase 1 training helps us configure the model with more specific StarCraft 2 actions. The second part of our fine-tuning was much more complicated. We needed a lot of game data. So we found an open source data set with replays of 36,000 game traces. So that's kind of the order of magnitude that you'd want for this sort of project. And the nice thing about this data set is it includes win-loss information, includes the actions, and it also includes essentially the screen snapshots. Because kind of a key problem is, how do we get in all of this rich multimodal visual information that the players are looking at? And the way that this is done is essentially by taking a multi-layered heat map over the StarCraft map. So kind of the first great blob area is just showing kind of what's the terrain for this snippet of the board. And then the other things are different heat maps showing the placement of different unit types. In our replay data set, we leverage two types of features: global features that have information about resources, upgrades, techniques, and these kind of spatial features. Now, at that point, we didn't have good success with any of the multimodal models, so we built our own kind of custom multimodal adapter using a vision transformer in BLIP2, and that essentially enables us to extract information about what's on the map. Then essentially what we can do is we can prompt the model in this way. I have kind of a generic part, but we can also have this game state part that has information about the current game status. And then we're training the model to output what the next 4 build actions should be. And we also look at a separate macro management task. We try to have the model predict whether that player is on a win-loss trajectory. The one thing I will definitely caution you about this kind of work is that we found that, at least for the Phi2 model, it is very important to translate any numeric data into categorical data. So if you give your LLM, that there are 7 buildings, you'll get a different response than there are a small number of buildings, a large number of buildings. You also end up finding that if you use too much numeric data, you'll end up consuming a lot of tokens in your context window. So for those 2 things, we kind of stuck to this simple categorical thing. Basically, what the model is, with all these LLM things, you're training the model in this self-supervised way to generate the prompt. So the model is given this prompt, and it has to kind of generate actions, and we score it based on its ability to generate actions. There was, of course, a lot of fine-tuning involved. We used LoRa and also the quantized LoRa version. It's very easy to do. We used the Hugging Face supervised fine-tuning trainer. Kind of a key thing was evaluating the performance of different hyperparameters. This can make a tremendous amount of difference. So LoRa has a couple of different hyperparameters, the rank, so essentially kind of how how much of the matrix you're trying to learn. And then the alpha, which is essentially showing how much is the weight change going to affect the initial weights. So then we look at results. So one nice thing about this kind of problem that's very different from our work with Lockheed, it's much easier to evaluate this kind of thing, because really what we're doing is we're looking at a couple of things. First of all, is the model good at predicting global state? Are we good at predicting and generating build orders? So we looked at our work, this LLM generation system, versus a gated recurrent unit model, a simpler transformer, and kind of a non-large language model transformer, and our model. And basically, I see a typo. It should be Protoss versus Protoss, not proton versus proton. The hazards of spell checking. Basically, what we're doing is we're trying to see how we perform at those two tasks. Now, we learned that none of our models are really that good at the win-loss prediction task. Our hypothesis is that we're not looking at a large enough time horizon to make that reliable, so we're pretty bad at that. We are very good at generating build orders, predicting build orders. So in all three matchups, you can see that we do outperform the previous work in this area. However, the neat thing about the large language model compared to all these specialized machine learning models is that they can do things that you didn't plan for them to do. So the question that we looked at is a transfer learning question. So assuming that you've trained exclusively on Terran versus Terran matches, and then you look at the question of, can you create build orders for a Terran versus Zerg match? How well do you do? So essentially the fine-tuned adapter is saying, how well would you perform if you fine-tuned for that case? Zero shot is saying what happens if you give the model no information whatsoever. But 5 shot, which is providing a little bit of context, you're providing 5 training examples, helps you a lot. So this shows that context really, really important for these things. So kind of to wrap up, kind of the things that you should remember are, yes, it's definitely very feasible to use large language models to do a whole variety of game-related tasks. My work has been primarily in these kind of planning style tasks, this work with Paul on behavior trees, and then also this work on build order optimization. One of my PhD students also looks at chess as well. So it's definitely very feasible. Context is really, really important for this. And either it could be done with RAG, this few-shot prompting. I think spatial, despite the emergence of these multimodal models, spatial reasoning still remains a really difficult problem for these models.
Yeah, and I'd add to, this partnership has been just incredibly valuable. You can tell why there's 2 people on the stage here, right? I've got the domain experience. She has the science behind the LLMs experience. And so I really appreciate the partnership. And I'll just, again, one last motivation in regards to, why we need this kind of capability is, if I go back maybe 20 years, I don't want to go back too far, reveal my age, but, we had customers that say, hey, we want to do wargaming at the battalion level. And that was the charter we were given. And we were not able to convince the customer that we could do it. We tried and tried. The best we could do is company level orders, right? And then so what that means, now we have to have role players, people that play the role of company commanders within the battalion, which is a gigantic amount of staff when you're talking about wargaming, right? You're trying to teach commanders how to do something, but now you've got this giant set of staff. And so part of the goal here is to reduce customer cost by simply reducing the number of role players involved in the game and instead just automate everything. So a lot of motivation to this. Thank you very much.
Mm-hmm.